Edexcel Decision 1, Linear Programming 2, Formulation of the Simplex Method. Introduction to the Simplex Method. The Simplex Method gives us an algebraic way of solving linear programming problems. In first year material, we looked at solving linear programming problems graphically, but this obviously has its limitations, as we can only solve problems with two variables in this way. So the Simplex method can be applied to problems with more than two variables, which is important for many real-world linear programming problems. It is an iterative method that seeks to maximize the objective function. And to understand how the method works, we'll look first at a two-variable problem and make use of the ideas we've already seen on solving graphically. The Simplex method is easily programmed, and in the real world, linear programming solver software is widely used. So we're going to just recap how to solve linear programming problems graphically. So here's a 2D linear programming problem with decision variables x and y and 3 constraints. So we want to maximize profit P. P is 10x plus 9y, and this is called the objective function. And it's subject to these constraints. And not forgetting our trivial constraints of x is greater than or equal to 0 and y is greater than or equal to 0, since many linear programming problems can't have negative solutions. So once we have our constraints, we need to draw the equations to find the feasible region for this problem. And as we can see here, we've got the feasible region enclosed by our constraints, and we've got 5 vertices. So these vertices are where the equations cross, and the optimal solution is one of these vertices. Now if we remember, these vertices are used to work out P, and one of these vertices will be the maximum value for P. So obviously this is the trivial vertex 0, 0, and this is when P equals 0. And then here we have the vertex 0, 10, and this would give us a profit of 90. Down here we have 10, 0, and this would give us a P of 100. Then we have 6 and 6, which gives a profit of 114. And then finally we have 8 and 4, which gives us a value of 116. So 8 and 4 in this example would be our optimum solution. So the Simplex method starts at the origin and systematically moves around the vertices of the feasible region, increasing the objective function as it goes until it reaches the one with the optimal solution. So the Simplex method solves the simultaneous equations for us, and it does this by manipulating rows in a table, and the rows in the table represent these equations. So solving two-dimensional linear programming problems graphically is fairly straightforward. But what happens when there are 3 variables? If we're thinking geometrically, this means we need to move to 3D space and draw a 3D graph. So what would the problem look like then? We're going to consider a typical constraint with 3 variables. 3x plus 2y plus z is less than or equal to 6. If we replace the inequality with an equality, we then get 3x plus 2y plus z equals 6. So what does this look like when plotted? So if you have studied equations of planes in pure further maths, you would have come across this. If you haven't yet, then you will do soon. So here we have the graph of 3x plus 2y plus z equals 6. And as you can see, it's a plane. So if we look at this linear programming problem here, we would have to draw all these equations graphically in order to be able to solve the problem. Solving this linear programming problem graphically would involve drawing many planes, as we can see here. So this time the feasible region is a 3D space. So the vertices can be found by finding the intersection points of the planes. So we can see on this diagram the intersection points of all these planes. And we would have to find these by solving simultaneous equations. The Simplex method involves moving around the polygon vertices to find the optimal solution. So here we have the objective function. The objective function is 4x minus y plus z equals some constant. And we can see that when we draw this on our graph, the objective function is now represented by a plane. So we can see that this is a fairly difficult task to do graphically. Whilst it's possible to get an idea of linear programming problems in 3 variables geometrically, solving using a graphical method is clearly not practical. It's not possible to extend these ideas to problems in more than 3 variables, and in fact algebraic methods have been developed to solve linear programming problems more efficiently, and we're going to see how the Simplex method can now be used to solve linear programming problems. So obviously, technology in the form of spreadsheets and LP solvers are widely used in practice as they are much more efficient and much quicker to do. In the next session, we're going to look at introducing slack variables.